Okay, so last time we left off with Bellman-Ford algorithm. That was an algorithm that finds the shortest path, and it also takes care of graphs that have negative edges. However, it does not work with graphs. Remember that it does not work with graphs that have negative cycles, right? So Bellman-Ford algorithm works with negative edges, but does not work with negative cycles. Okay, so let's look at the algorithm um, uh, in a bit more detail, and then we will go through a dry run about for this particular algorithm. So the input to this algorithm is essentially a directed graph, call it G. The length of those edges. So essentially we are talking about weighted edges. Remember that BFS algorithm and DFS algorithms did not account for edges that can have certain weights. And the moment we add weights to our graphs, we now need to redefine what shortest means and how we traverse and explore our graph in the first place. So essentially, we want to explore our graph along the path that takes up the shortest length. And that is where these weights and other things come from. And essentially, as we discussed earlier, weights in graphs are quite natural in general, because if we have multiple vertices in our graph, or we in the real world, we can be guaranteed that multiple vertices are connected to each other with different weights, right? So that could be the graph connecting multiple cities, and then the weight of the edge can be the edge length can be the distance between two particular cities. Or we can also have other scenarios where we can have certain decisions to be made, and making one decision is more costly than making the other decision. So we need to also take into account that particular situation as well. So given a graph, given the length of the edges, and given a starting vertex S that belongs to the set V, what we need to figure out is the shortest path starting from S to all other vertices from S, right? So this is a single source shortest path algorithm, right? Okay, so Bellman-Ford works similar to our previous algorithm, that is the Dijkstra algorithm, that also took care of graph weights or edge weights as well. But it additionally takes care of edges where edges can have negative weights. The only thing that it cannot work with is where we have a negative cycle in your graph. And if we have a negative cycle, then everything else goes out the line. So we don't care about those sort of scenarios. But we do care of scenarios where certain edges can have negative weights, and Dijkstra cannot handle that. However, Bellman-Ford can.
What was the reasoning as to why Distro couldn't handle any negative weights in the graph?
Okay, give me one sec.
Just as a review.
Yes, so this was the example. So there are multiple reasons, but the main reason is Dijkstra, once it takes care of a set of vertices, and since Dijkstra is just a more, so Dijkstra just adds the capability of adding weights to graphs from your traditional BFS algorithm, right? So you have your traditional BFS algorithm that takes one node at a time. So let me go back to that particular representation. Give me one sec. Not this, not that. Where was that? Yes. So remember that Dijkstra just accounted for the first starting vertex, and then just explored every vertex that is connected to it. So in this case, it was the starting vertex was S, and then it explored ACDE. And once it did explore ACDE, then it moved forward to B, because it was using this queue architecture, right? So ACDE gets explored first. So all the vertices that are connected directly to the source vertex and the following vertices get explored first. Now that was the reason where we accounted for all edges being the same weight as weight 1. Now let's say that we have a negative edge in case of a graph. Let me just bring that up. It was the triangle graph. Okay, so in this particular scenario here, Dijkstra would have started from the vertex S. It would have covered both it would have looked at both A and B. And since A had the shortest distance here, remember that Dijkstra is sort of a greedy algorithm and it is going to look at vertex A first. And since A has the shortest distance, it assigns A with the distance of 3. And then it moves forward to B, it assigns B with the distance of 4. So A has 3, B has 4, and Dijkstra did not account for negative edges. And since it did not account for negative edges, we have an edge that goes from S to B and then B to A. And this particular distance became 2. However, Dijkstra did not account for this particular thing because it always accounted for positive edges. And so Dijkstra would not be looking at A because A has already been visited, and all visited edges or all visited vertices would always have a distance smaller than any other, than if we find another path to that particular vertex, because all the paths other than the path found by BFS would be longer. So imagine that this -2 was a positive number, right? So imagine that all edges are positive edges. In that scenario, if we explore using BFS, we would cover the first set of edges, first set of vertices, and the next set of vertices, and so on. So if we do find a path that connects back to a particular edge at the very front, in that scenario, since all vertices are of positive numbers, then in that scenario, then that particular path would be longer than the path we have already found. And since Dijkstra does not take into account this particular scenario where a path can change, so Dijkstra always assigns, in terms of BFS, Dijkstra would always assign the first discovered edge length as your distance, because BFS guarantees that you are going to always find the shortest possible path. If we find that particular vertex again, it is guaranteed to have a longer length, right? And that is why Dijkstra does not account, and Dijkstra basically ignores that particular vertex. However, if we have negative edges or negative weighted edges, it could be that once we find another path to this particular vertex, let's say in this scenario A, we find that the path is 4 minus 2, that is 2. However, Dijkstra just says that I have already searched for this vertex, and I have searched for this vertex in terms of BFS, and I'm not going to update this vertex anymore. And that is why we needed Bellman-Ford instead of Dijkstra, because Dijkstra did not account for this particular scenario. Does that make sense?
Right, because you're basically saying like, hey, based on Dijkstra's, you say like, oh, we're already done
Yes.
updating. We have the optimal path to A, but then you can't just come back later on and say, oh, well, actually, this is a better path because
exactly.
Okay.
Because imagine this thing. Imagine the scenario that we only have positive weights, and since Dijkstra is basically the BFS algorithm with weights, right? So if we apply a BFS algorithm, we know that the moment we find a particular vertex, we are guaranteed to find the shortest path from the source to that vertex, right? Because all of them are positive edges. So if Dijkstra finds another path to that particular vertex, and since all of them are positive, it is guaranteed to be longer than what we have found so far. So Dijkstra doesn't even check for that. And exactly, you are correct that is why Dijkstra cannot handle negative weights. However, in order to handle negative weights, what would we need to do? We need to update A again, right? So this particular vertex originally had the length 3. However, if we were to apply an algorithm that can allow negative weights, we need to allow updating all vertices we have visited so far, such that in case we found another path which had negative weights and that can have a smaller length, we need to update that vertex as well. Dijkstra does not do that, Bellman-Ford does.
Okay, but the drawback is now we're kind of backtracking and it's going to increase the time complexity of.
Exactly.
Okay,
Now that we are backtracking, we need to update every vertex every time, and that adds to our complexity. Exactly. The main reason is Dijkstra basically looks at this particular equation, right? So either the distance we have found so far is minimum, or the distance we have looked up till one plus edge to from that source parent vertex to this vertex. This needs to be either one of those two numbers. It does not account for all vertices that can go around and come back to this vertex that can have negative edges. So that adds more complexity to our algorithm, but also allows us to have negative edges as well. Exactly. Okay. Yes, so Brian Akins. So yes, it is not updated based on the best. It is updated based on the first time we discover a particular vertex, because underlying this particular algorithm is the BFS algorithm that sort of guarantees that we are always going to find the minimum most distance. And this minimum most distance works in case of graphs where we have unit weights for our edges. So if we discover the next set of edges, we know that we just have to add 1 to those edges, and that is the correct distance. If we find down the line somewhere and we find another path that turns back around to this vertex, we know that we are going to add up those distances, and then that cannot be the most minimum value. And so it is essentially the best because it is the underlying principle is BFS. However, best becomes difficult when we have negative edges. Exactly. So yes, Brian, you're correct. Dijkstra does not update if it finds a better path, because it always assumes that since we are using BFS, it is going to find a vertex that always is on the better path. And that is guaranteed. Why? Because it is all positive edges. So does everyone understand why, if we have a graph with all positive vertices or positive edges, the first time we encounter a vertex, it is going to be the shortest distance if it is all positive. You can say no if you don't understand the question. I mean, I need to know.
that can you go a little deep? I guess I look at that distance v comma distance u plus cost of u to v. It seemed like you would potentially update past the first time you.
Yes, however, remember that we are considering UV to be a part of the edge list. So U needs to be the parent of V. It cannot be a longer path that comes back to this particular vertex. So this particular distance is always updated, and once it is visited, we do not care for this particular vertex anymore. So let me just find the algorithm, right? So remember that in case of Dijkstra, we are creating this known region, right? So the moment we have a vertex that is added to this known region, we do not care about this vertex anymore. But for Bellman-Ford, that allows us to update all vertices even if we have found it before. Okay, so let me explain. Bellman-Ford allows us to update vertices even if we have found a particular vertex before. Dijkstra does not allow us to update vertices if we have found it before. Does that part make sense? Because we are picking a node that is not part of this known region, so to speak, or this visited set of